Welcome back, everybody. We're going to be starting the last section before exam one. So I'm going to actually share differently. I'm going to share, where is it? Where's Desmos? There we go. Uh, Not this. Don't worry, we're gonna get that. So just looking at the course calendar at the moment. So today is 12-12. I forgot to tell my other class. So I hope everyone has a good Valentine's Day. And then not trying to rub it in if you don't have a Valentine's, but just wanting to wish you guys a good break. True. Good way. Good way to think about it.
What is that Miley Cyrus song? It's like I could buy something flowers.
I can buy myself. There you go. Indeed. So we have today and then we have next Wednesday because President's Day is on Monday. Just as a reminder, we do not have class on Monday. No CSN classes on that day. So you don't have to come to campus at all. Yeah, we do not have class. And so the following week after President's Day and Wednesday, then we have our first exam in week 6. It's on Wednesday in class, free response. Maybe like I'm toying around this semester with adding some like maybe some true false things, but probably not. But we have the review day. I will be posting sometime during week 5. I'll be posting an exam review that you can utilize. Usually the way I do them is I put I give you the review sheet and it'll have like several different problems on it. And then at the very end, it'll have the answer key. And then a separate document will be the solution guide. Answer key is just the answers. Solution guide is how to do the problem. Now, when I do that, my recommendation and kind of my expectation is that you try the review first yourself. Do not look at the solution guide until after you've attempted it at least once. Because speaking from experience, if you just look at solution guides, that's not you learning how to do the problem. That is looking at someone else and realizing how their thought process works, not how your own thought process works. So my usual go-to is try the review, check your answers. If you got it right, kudos, move on. If you got it wrong, try it again. Like maybe study back up and try again. And if you still get it wrong, then look at the solution guide and see where the mistakes were. Then try it again fresh and recreate it yourself. That's the best way to learn from a mistake, quote unquote, is to see how it's properly done and then do it in your own words. That's going to make you a much stronger mathematician. But this will be the last section. We'll finish it. We'll start it today. We'll finish it on Wednesday of next week. And then I don't think we'll have to do any catch up on Monday on the 24th. But in case we do, we'll finish it there. Otherwise, we'll just spend the rest of that time just doing review. Ideally, the way I kind of run my review days is there for you to ask the questions that you want to know. I might pop up questions, but I don't have anything generated. I don't have anything like that I'm ready to go over on a review day. That's for you guys to ask questions because ideally you've been studying and you have like some curiosity. Like it can be as simple as, can you go over something from section 1.4 or 1.5? But I'd like you to be ready on Monday to have an idea of what you want to go over, the weak points in your armor, so to speak. Okay? Any questions on that? Yes, Brian. So not a practice exam. I don't usually believe in them, but I will make a review. So it's just going to be a collection of questions. It's not the same length as the exam. It's probably going to be longer because it's going to be more questions. And my mentality that I've had since I took Dr. Taggart's class at UW was that if you can do the review, you should be prepared for the exam. If you can do the review with no difficulties, you should be ready for the exam.
How many questions would you have?
I mean, last semester I did 300, so probably 400 this semester, just make it harder. No, the thing is, it does not matter how many questions. I'll tell you, it's usually anywhere between 5 and 7 pages. I promise you, I design my exams so that they are doable within the time limit allowed, along with ideally about 5 to 10 minutes to review your answers. So as long as like that's the way I write them down, I test them myself using a little algorithm that I've figured out to see how long it should be. And then I check it with my wife to make sure that I'm not asking anything that's too ridiculous because I get carried away.
If you don't finish our exam, can we like come back later and do it?
No, it has to be done in 1 hour and 20 minutes. And that's partly because I want you guys to be prepared for the final exam for this class is partially departmental. There's several questions that need to be on it. That are like, I mean, question like variables may change and stuff like that, but there's gonna be several questions and I want you like that has a strict time limit because it's a departmental requirement. So I want you guys to be prepping for that time limit. Eli.
Study that and we get it all correct. Is it enough?
I mean, I'd say like it's very rare in my experience that a person does the review and says like, no, I got it. It's on lockdown. So like usually when I do a review, I'm like, okay, that's the part where I'm a little rusty on, so I'm gonna brush up on that. It's a good means of study, but it's always a good idea to kind of check over your homework, check over your exam, like check over your quizzes that you did, check over your notes and things like that. But you can always look up more practice problems online as well. Any other questions? Did you have one? Did you raise your hand? Okay. Brian, yes.
So if we need to practice on like something that I'm having difficulty getting, where should we go to practice those questions?
Excellent question. Where can we go? One of my favorite places is Khan Academy. This is one of the greatest websites that's ever been created. Sal Khan is the person who created this website. They started off with just math videos, but it's been expanded to chemistry, to basic math, to computing and so on and so forth. They've actually even partnered. They're like really. Sal Khan's written a book about AI and how it should be embraced. But
They have like an SAT.
they have so many resources, and so all you really need to do is like let's say radians. Like I can find radians and degrees, and I can find lessons on that, and each one of those things usually, if memory serves, they usually have practice problems that come along with them. So yeah, practice, and you can convert it to radians, so on and so forth. So just search the topic. Ideally, something will pop up that looks similar, and then like you can look at it and based on the material, you can say like that's similar, so I can get more practice problems. Khan Academy is a great resource. Say what? Oh no. Yeah. Cool. Any other questions? All right. Let me go ahead and stop sharing and switch back over to the iPad. Oh, wait, it switched over. Awesome. Okie dokie. And here we are. So now we're on to the graphs of sine and cosine, because what we've just realized through all this work is with coterminal angles and reference angles and being able to find the points on any point on the unit circle is that you can find sine and cosine for any value. In particular, that means that you could create a graph. Instead of using theta, we could make it x, like the independent variable, and the y value, like the sine value or the cosine value, would be the corresponding dependent variable or the y variable. So I got a unit circle here for us to go through and plot them. So the graph of sine. So we're going to plug in several points. Specifically, we'll try and just point the spokes because those are the nicest numbers, right? Square root 3/2 is like 1.7. It's not a very good number. Sorry, not 1.7. Square root of 3 is like 1.7, but square root 3/2 is like point whatever it is. Doesn't matter. So those are really hard to graph on a number line, but the fact of the matter is with the spokes, it's always going to be 1, 0, or -1. So at -2 pi, so remember this is 0 degrees slash 2 pi slash -2 pi and so on and so forth. So at -2 pi, and this thing is starting to wig out, so I'm gonna have to shut it down. I think I've got too many files on this. I need to like wipe out some of the stuff. But either way, it doesn't like how many PDFs I've uploaded. So sine of 2 pi, a -2 pi would be 0. And that means we have the point -2 pi comma 0, -3 pi over 2. So just kind of drawing it on the graph, -3 pi over 2, negative pi over 2, negative pi, negative 3 pi over 2. Up there, sine is the y value, so it's 1. Then negative pi would be here, which would be 0. Negative pi over 2, that's right here. So that's going to be a y value of negative 1. So sine of negative pi over 2 is negative 1. Then 0. And then pi over 2 would be 1. Then pi would be 0. 3 pi over 2 would be negative 1. And then 2 pi would be 0. So just fill in the points then. That's interesting. It just keeps oscillating, just keeps repeating itself over and over and over again. Just keeps going from 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, and so on and so forth. And so the graph of sine, then, we can figure it out from this information. We can plot all those points. So I got a nice graphing grid here that's already broken down in terms of pi over 2s. So that would be, so negative 2 pi, it's 0. Then 3 pi over 2, it was 1. And just to make it look a little bit better, let's make this 1. So then it'll go up to 1 right there. Then at pi, so negative pi, it's 0. Negative pi over 2, it's negative 1. Then 0, then 1, then 0 at pi, then negative 1 at 3 pi over 2, and then 0 at 2 pi. Let me make those like the hash marks for those a different color. That's making it look confusing, in my opinion. So now, several points isn't enough to graph things, but it is enough to sketch it. And what you'll end up seeing is that the graph, if you were to try and plug in like sine of pi, like we know that sine of pi over 3 is square root of 2, and sine of 30 degrees or sine of pi over 6 is 1/2. So we could plot those two if we really wanted to. But either way, the more you plot, you start to look that it looks like this cool squiggly line. Whoop, 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 like that. That is f of x equals sine of x. Or y equals sine of x. Remember, y and f of x are synonymous. It's been a while since we talked about function lingo. But remember, functions are just replacing y with f of x, just to make it so that we can see what we're inputting into the function. Bless you. Any questions on that so far? The next one, so for cosine, that's just going to be all the x values, because cosine represents the x values. So at negative 2 pi, once again, that's negative pi, negative 2 pi. So it's the x coordinate there, which would be 1. So we have negative 2 pi comma 1. Negative 3 pi over 2, that's going to be 0. At negative pi, it'll be negative 1. At negative pi over 2, it'll be down here. And the x coordinate is 0. It's going to be 0 again. And you're going to see that it repeats itself very frequently. 0, it's going to be 1. Pi over 2, it's going to be 0. Pi, it's going to be negative 1. 3 pi over 2, it's going to be 0. And then 2 pi, it's going to be 1. And then it'll just keep going on and on and on and on forever like that. And as we remember from the triangle definition of trigonometry, remember sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. The hypotenuse is always the largest side of the triangle. So regardless of what the leg is, regardless if it's the adjacent or the opposite, that side length will always be smaller, right? It'll always be smaller than the hypotenuse. So meaning that it'll always be less than 1, the fraction that it makes. And that makes sense when you look at the graph now. The graph has a maximum peak at 1s and a maximum valley or a minimum valley at negative 1. Same thing's going to be true for cosine. So if we plot these, and this time I'll use green. So negative 2 pi, and then we're also going to do the same thing. We're going to make the second hash mark a positive 1, and the second hash mark down below a negative 1. And so at negative 2 pi, it was 1. At 3 pi, negative 3 pi over 2, it was 0. At negative pi, it was negative 1. At negative pi over 2, it was 0. At 0, it was 1. At pi over 2, it was 0. At pi, it was negative 1. At 3 pi over 2, it was 0. And then at 2 pi, it was also 1. So it looks roughly like that. Now I want, like, there's going to be a section where I mention this. They look very similar, don't they? Look very, very similar. In fact, just as a weird thing, what if I just, it seems like cosine is just sine, but shifted to the right pi over 2. Or I mean, you could even also say shifted to the left by pi over 2, or 3 pi over 2, for that matter. So that's interesting. That's an interesting observation. Maybe there's something there. So this is f of x equals, or let's just call it g of x, just to make it a different function. Just have some fun. I love functions. Functions are my favorite concept in mathematics, and I don't know if any of you guys actually took me for 126 or 126E, but you know why functions are the best concept in mathematics, right? It's got fun in the name. How could it not be the best concept in mathematics? They're the most fun thing in mathematics, just by definition. Anyways, but the reason why I bring up functions, you may have talked about this in 126. We typically kind of remove it, at least I do, because it's not really a very relevant or useful concept other than this just one fact. Have you guys heard of even and odd functions? Cool. I don't teach it because it's not really that useful. But the one thing, it's a useful fact that I'm going to put up here. It may just save your life one day. Is that f of x equals sine of x is an odd function, which means, so an odd function means that it's symmetric with respect to the origin. And so that means that if you have the point a comma b, you have the point negative a comma negative b. But in practice, what this means is that sine of negative x is equal to negative sine of x. So if you have a negative on the inside of the sine function, you can bring it outside immediately. That's just a nifty little trick that we can do. And the second one is that g of x equals cosine of x is an even function. Which means that cosine of negative x is equal to cosine of x. So cosine just repeats itself backwards and forwards. It's symmetric with respect to the y-axis. That's a very useful trick, especially later on in your mathematical career. You use that somewhat regularly, especially if you plan on taking like 283 and beyond, sorry, 285, which is differential equations. I can't remember if here I know what it was at OSU and UW, but here 285, I don't know if they go into it, but you'll start studying things called Fourier transformations, and Fourier series and Fourier transformations all have to do with sines and cosines. So this isn't just some one-off concept. It's actually a fascinating thing. If you ever want to know about it, Fourier, very, very famous mathematician, he showed that any function, you don't need to write this down, but can be written as a sum, a sub n sine of n pi x over L plus b sub m cosine of m pi x over L. Every function you can think of, every function, no matter what it is, you can write it as a sum of sines and cosines, which is bonkers. That's amazing. that like any function you can think of, like square root x squared minus 3x divided by natural log of x minus 5, you could write that as a sums of sines and cosines. An infinite sum, of course, which makes things a little bit wonky, but Fourier series, super cool. If you want to know more about it, please feel free to talk to me. That's in an area of mathematics called functional analysis. So anyways, I'm getting sidetracked. Sidetracked. Anyways, so with that in mind, some of the properties of sine and cosine graphs. So you just saw that picture. And so one of the things that you notice is it repeats itself a lot. It oscillates back and forth and back and forth. And we call that a periodic function. And the period of a periodic function is the length, the distance of x that's required to complete one cycle, i.e. the length from one point to any other matching point on the next cycle. In particular, so there are plenty of other types of periodic functions, but sine and cosine are the most common. And so for those ones, you can look for from peak to peak, or from valley to valley. That's a good one. Or from origin to origin, or a center to center. So one way, this is from a valley to a valley here. And then you could also do it from a center to a center. And then one thing that that threw me off as a student, because like it looks like it's the same point. So shouldn't this be a period too? But it's not, because it's not the same spot. Notice that this spot you're going up, but here you're going down. So the period actually would be a little bit past that. It would be right here. That's one period, because it's where it starts doing the exact same process. Does that make sense? It's not enough to be the same point. It's where it starts back over again. So the point that I wanted to make there is that you can measure periods wherever you want. It doesn't have to be at the origin. You don't have to start measuring it at the origin. You don't have to start measuring it at a peak. You can do it wherever you want. But just for the most useful aspect for sine and cosine is either from peak to peak or from middle to middle. And not this middle, right? Because this one, you're going up and then going down. You want to go up to up. Okay? So in particular, with sine and cosine, just sine of x and cosine of x. We're going to talk about more in detail in a little bit, the sinusoidal functions, as it were. But for the basic sine and cosine functions, their period is 2 pi. So then we have these new names, and I'm gonna blow your mind like when we get to what part is it? It's 1.5.3, so in about 3 pages. So I'm gonna make you go but we're going to have to call them new names, apparently. So the amplitude of a sine or cosine graph is the vertical distance from the midline to the highest point or the lowest point on the graph. So it's the vertical distance from the lowest point to the midline, or half the distance from the top to the bottom. So this right here is the midline. The line goes straight through the middle. And so the reason why it's half the distance from a peak to a valley is that you've got 2 amplitudes equals the distance from a valley to a peak, or a peak to a valley. So the amplitude is half of that. It's how much you have to go up or down to reach a peak or a valley, respectively. Now, when it comes to sine and cosine, just the original functions, as we saw, that would be a distance of 1. And once again, this makes sense because -1 is less than or equal to sine of x or cosine of x. Sine of x and cosine of x are always bounded between -1 and 1. This is going to be a useful fact later on when we start talking about inverse trig. But for now, and it's also very, very useful in calculus at some points, especially when you talk about a thing called the squeeze theorem. Just a silly name for a theorem, but it's a very, very useful one. Surprisingly, it gets used in the proof of the fundamental theorem of calculus, but I'm getting sidetracked. Well, key point is that sine and cosine are bounded between -1 and 1, so the amplitude should be 1. It can either go up 1 or down 1. The next thing, and we've already seen these before, but vertical shifts. You can shift a graph up or down. So this was the original graph of sine because it starts at the origin and then goes up and down and up and down. And a vertical shift would just move it up or move it down. This one's moving it up, but normally it's moving it down. Or it could be moving it down. Excuse me. So with sine and cosine, there is no vertical shift. So the vertical shift for y equals sine and cosine is exactly 0. And the midline, we mentioned it, but we didn't give it a full specific name yet. So the midline of a sine or a cosine graph is the horizontal line that runs halfway between the highest and lowest points. It's right directly in the middle. It's where we decide where the amplitude is decided upon. And so please remember that it's a dashed line, meaning that it's not actually part of the curve. It's just there for reference for us when we're graphing it. So the midline for y equals sine of x and y equals cosine x is it's going to be right here. So John Doe student writes this. Why is John Doe student wrong? What is a line? It's an equation. It's a function. So it has to be y equals 0. The midline for sine and cosine is y equals 0. The next thing, there was a typo in the notes. I forgot to change it. But the phase shift is just a horizontal shift of the function. It's just a new cool name that makes it sound way cooler because we're doing trig. It's a phase shift. It's not a horizontal shift. That's lame. It's a phase shift. And in this sense, because you know now it's so cool, set phase to stun, right? For any of my Star Wars fans out there. That should be upsetting to you if you understand the joke. This Star Trek and Star Wars is getting mixed up. Anywho, I'll skip that one next time. So, the original graph would look like this orange line. So remember, it's periodic. It repeats itself over and over and over again. So, but the phase shift this time, it shifted it to the right some known units. And so we've got, this is the original, like the orange is the original graph of one period. It's down there. And this is the new graph of one period. So it is possible for your phase shift to actually end up making it exactly the same. So case in point, once you're finished writing that. So just going back to this picture here for a second. So if I were to take this graph, right, like that, if I phase shift this thing, if I move this pi units, that's 2 pi units, excuse me, you see that it ends up making the exact same graph. So there is a nifty little interesting point there, but either way, phase shifting can look like the same graph. It doesn't actually usually happen, but it can happen. Very rare though. And so the phase shift for sine and cosine, they don't have a phase shift. They're just 0 when you start with them. Well, that's what a phase shift is. It's moving it left or right. Now, I deliberately picked those points, the spokes, I deliberately picked the spokes for a good reason. It's a very nice way to complete the graph of sine or cosine, because those are the nice 1 or -1 or zeros. If you really want to start graphing like the 1/2 and the square root 3s over 2s, you be my guest, but it's just unnecessary work. So that leads us to how you can graph it very quickly. Instead of having to sit there and plot several points, you can do it by finding the key points on a sine and cosine graph. The key points are the specific locations to help you accurately sketch it using one complete cycle of the wave. These include the starting point, i.e. the beginning, which is the phase shift, the midline intersections, the maximum points, the peaks, the minimum points or the valleys, and then the ending point of one period. So in this class, we will typically just draw one period of the sine or cosine curve, or tangent curve, or cotangent or cosecant or cotangent curve. We'll typically just draw one period because it repeats itself over and over and over again. Why do we need to draw more of it? So the key points for sine, it will always start. So this is not an original sine graph, right? This one does not start at the origin. So this one has been shifted one unit, some odd amount to the right. But you've got the places where it intersects the midline, which specifically also includes the end point, the starting point and the end point, and then the peak and valley that are in between it. For cosine, you have the two peak points, the one valley point, and the two midline points. So the shape of them is precisely that. A cosine period graph should just be this orange piece that looks kind of like a weird smile, right? And this one's just this squiggly line. The quintessential calculus graph is what I like to call it. And with regards to the shape, cosine will always either start at its highest point or its lowest point, depending on the coefficient. A positive coefficient means you're going to start at the top and go down and then back up, whereas a negative coefficient means you're going to start at the bottom and then go up and then back down. So for example, right here, this one here, it could be y equals positive cosine of x, or it could be like 5 cosine of x, positive 5 cosine of x, because I didn't give any scaling on the y or the x-axis, so it's impossible to know. But the negative cosine starts at the bottom and then works its way up top. Any questions so far? Next thing, for sine always starts on the midline when we're graphing a period. But that's not this. I mean, so when we're graphing it, when we graph it to make it look nice and neat and pretty, we always start on the midline. But there's nothing stopping you from, I guess technically speaking, you could start here. Oh, I use a different color. You could start up here and draw it like that, but convention says that you should start at the midline to draw a graph of a sine wave. But the direction on which you go up or down has to do with whether the sign in front. If it's a positive coefficient in front, so like sine of 1x, or other examples. Ooh, I should have written that up here too. So other examples will be something like f of x equals 2 sine of x. And another example here, or I'll use red. Would be like f of x equals negative 1/2 sine of x. So with negative ones, they start at the midline and they go down, then back up, and then back down to the midline. So some other examples here, just so that we've got some examples. Something like y equals 5/3 cosine of x. And some other examples here. Be something like g of x equals negative 10 cosine of x. Sorry, I ran out of space. And I'm just using different names of functions just to remind us that you can call a function whatever you want. You can call it Y, you can call it F, you can call it G. You can even use any, like, it's any symbol, really. You really want to, you can do delta of X. You could do that. Or because it's just a variable, you could do a puppy dog of X equals cosine of X. That is possible. You could do that. It's allowed. It's the funny thing about mathematics is that it's just a variable. It's just a symbol. But anyways, I'm getting sidetracked. I just wanted to show you how good I am at drawing puppies. I'm not very good at all. So then we get to what we call sinusoidal functions, or the general form of a sine or cosine function. Sometimes, so I'll put this up top here, sometimes called sinusoidal functions. But why not also cosinusoidal functions? Because as we saw, you can just shift it back and forth. So the general form of it would be a sine of bx plus minus c plus d, and then a cosine of bx minus c plus d. So all those things we just learned, the period, the amplitude, the phase shift, the vertical shift of midline, and then some new information, the quarter period, which I'll explain in a second, an interval to draw an interval for one period. Would be from the phase shift to the phase shift plus period. And then the domain, because it's a sine function and cosine function, and they're defined everywhere, the domain is all real numbers or negative infinity to positive infinity. And then the range of them will be d minus the absolute value of a to d plus the absolute value of a. So just, it's been a while since we talked about domain and range, because that was last semester or prior, depending on when you come into this course. But since a could be positive or negative, that's why it's d minus the absolute value of a. So that we know, like, we put the more negative number, the more left number first, and then the more positive number second. Okay, I thought that was mine. But yes. So the formulas are that the amplitude will be the absolute value of a. And that kind of makes sense when you think back to this situation with amplitude. It should be how much, like what it is at the very, very top when sine is 1. Because when sine is 1, it'll be a times 1, which is just a. And when sine is -1, it'll be a times -1, which would be negative a. So that's why the amplitude is the absolute value of a. The period is like how you determine the period of a sinusoidal function of one of these ones is 2 pi divided by b, the constant in front of the x. And that's because you told me to, right? SpongeBob or Patrick with the when he's what is he holding? I forget what he's holding, but it's because I said so. That's why it's 2 pi over b. Now I'm going to explain the reasoning. And then the phase shift is going to be c over b. And the thing is, c over b positive implies shift right. Yes. And if c over b is negative, we're going to shift left by that amount. The d value is your vertical shift. It's how much you're going up or down. D positive. You're going up, and D negative, you're going to go down. And the quarter period is going to be, this is going to be used to plot your quote unquote stepping stone points. The quarter period is going to be allowed, is going to allow you to graph your stepping stones. And I'll explain that in a second. And then the interval and period where I talk, like the interval where I'm talking about that, we're only really interested in one period of the graph. So we only really need to draw it from the phase shift to the phase shift plus one period, because it'll repeat itself every period. Any questions so far? Yes, Eli.
I didn't get.
You didn't get that. Absolutely, that's fine. Let me ask a follow-up question. Is it why is the period 2 pi over b? Why is the phase shift c over v? Is it those types of questions? No.
I don't know.
It's a lot to take in. There's a lot here. So we're going to take time to explain each one of these things because this is the mind-blowing part. Ready? Ready? What was your guys' favorite section of Math 126? I know everyone's going to say it at the same time. What's the most fun part of 126? Transformations of functions. You guys remember that? Remember? This is just mind blown. These are just linear transformations. That's all this is. Bet you didn't expect to see it again, did you? Saying, oh, thank God I don't have to deal with that after exam 1. Nope. It shows up again and again. Not too much. It's going to start dissipating over time. And then you have to talk about it in terms of matrices, which is not fun. But it's just a linear transformation. When I have, if you remember, so you don't need to draw this down. This is just for observational purposes. So if this is the function f of x, when I what was the function y equals 2 f of x? That was a vertical stretch because what we did, remember, f of x represents the y value. So if I double the y value, it means that I'm stretching it vertically. So this one would be, it would go like this. And so that's what the amplitude's doing. We're multiplying it in front of a sine function or a cosine function, so it's stretching the graph or shrinking it, because we could also have something like 1/2. Not green, I've used green, so orange. Y equals 1/2 f of x. What that's going to do is, because that 1/2 is on the outside of the function, that means you're taking the y values, the f of x, the function values, and you're halving them. So you're going to compress it. You're going to compress it down. So what this would look like would be something along the lines of this. Does that make sense? So that's why the amplitude is the a value, because that's how much it's going to stretch the graph or shrink it, depending on the size of a. Now, the reason why it's the absolute value of a, I'm going to keep drawing this. This is just like, we don't need to take notes about this. We just need to pay attention. So once again, I'm going to draw the quintessential calculus graph right here this time. This one. This is f of x. The reason why it's the absolute value of a and not just a, because remember, if a is negative on the outside, what is y equals, let's use red. What is y equals negative f of x? That's a reflection. Remember, you might remember there's the 2 different types of reflections. There's the reflection across the x-axis, and there's the reflection across the y-axis. But this one is flopping the y values because it's on the outside of the function. So this one gets reflected across the y-axis. But regardless of how you're measuring it, it's still the distance from the midline. So we want to put the absolute value signs in front of it to make sure we just choose the positive version of the number. The minus sign won't actually change the distance from the midline. It just makes it flipped. Is that okay? Any questions so far? So that's how amplitude is being defined. Amplitude is just another name for a vertical stretch or compression. That's just all it's doing. It's just stretching the graph or pushing it together. Now, going back over to, and this we're going to actually write down in a second, but the period, why is the period going to change by b? Why is so a sine function has a period of 2 pi. Why do the sinusoidal functions, where b might be 1, it might be 10, it might be 30, why does the period become 2 pi over b? So we're going to add that down right here. Why is the period equal to 2 pi over b? Once again, it is a translation. It is a transformation of the graph. So when you have this bx minus c, this b is a horizontal stretch / compression. So it will stretch or compress the graph based on what the size of b is. Stretch / compress the graph horizontally. Now, the thing is, one thing to know is that if b is greater than 1, so you don't have to memorize this. Like if you memorize the other formulas, then it kind of falls out nicely. But if b is greater than 1, it's going to shrink it. And if b is between 0 and 1, it's going to stretch. I meant to write compress, not shrink. I disagree with the terminology of shrink. And now, by the way, I'm also going to I'm going to switch over to my computer screen for a second after we write this stuff down and go through this first example, because I want us to kind of observe it all happening in generic terms. So why is the period 2 pi over b? It's because if b is greater than 1, you're going to compress the graph. So it's going to get shorter. It's going to get smaller, which would make sense. If 2 pi over b, if b is greater than 1, it's going to start making that number smaller, right? This is the classic thing that students, well, Americans in general, don't realize is if I've got a number, if it's a larger number here, the result is a smaller number, right? The bigger the number in the denominator, the smaller the overall number, right? Whereas if it's a smaller number, like a number less than 1, it's going to make it larger, right? And so this is that whole thing. If you didn't know this, A&W, the great root beer company, they don't just sell root beer. They actually have restaurants. They have fast food chains, and they were trying to compete with McDonald's quarter pounder, and so they made their own thing that was a 1/3 pound of beef, but Americans thought that was less than 1/4. America, right? We made that mistake. So it didn't do well because we thought that 1/3 was smaller than 1/4. Yay. So the point being, the larger the denominator, the bigger the b value, the smaller the period, because it's going to get shrunk. It's going to get shrunk and smushed together. Whereas if you go with a number between 0 and 1, right? Think about if I have 2 divided by 1/2, that's going to become 4. So if I divide by like 1/2, I'm going to stretch it double time. If it's 1/3, I'm going to triple it in length, in width, not in length. Any questions on that? Does that help kind of explain period and why it's 2 pi over b? I hope it does. And we can always ask questions. So that's why the period is 2 pi over b. It's just a linear transformation. Now, the next thing, the phase shift. Why in the name of Christ is it C over B? Why would that be the answer? Why would that give us the phase shift? So that's the next little subsection I want to draw down here. So why is PS, so phase shift PS, equal to C over B? So this one requires us doing a little bit of algebra. So you've written that down. So the reason why I'm doing this because this is the way the book does it, but I actually fundamentally disagree with this format. I believe that a sinusoidal function, maybe I'm the only mathematician who thinks this. I complain about it in my department meetings, and everyone thinks I'm just crazy, which is true. But regardless, I think sinusoidal functions should be written as this: a sine of b times x minus c, like that, plus d. Because with linear transformations, that makes way more sense, because that tells you exactly where the movement will happen. But regardless, so if it was like this, C will represent the phase, will be the horizontal shift. But that's sadly not the way the book does it, and most books teach it this way for whatever reason. They're wrong, but that's okay. So the reason, though, is if you take bx minus c and you factor out a b, this becomes x. And then remember, if you factor something out, you divide every term on the inside by that number. That's when that's why if we have x cubed minus x squared, when we factor out the x squared, what's really you write x minus 1. What happened? We divided x cubed by x squared, and we divided x squared by x squared. So the point being is something we sometimes forget is that you can factor out any number you want. It doesn't have to be a nice number that's a GCF. You can factor out anything. And so the point being, if I factor out a b, then each term on the inside gets divided by b. So bx divided by b, the b's cancel. And then you have c over b. And this right here is a horizontal shift by definition, and by c over b. And if you remember anything about linear transformations, was anybody so I actually want to ask this as a general consensus. Did you guys hate doing the horizontal stuff? Because the horizontal stuff was always counterintuitive. Vertical stuff just made sense. If I add d on the outside, it goes up. If I subtract d on the outside, it goes down. But with inside stuff, with stuff having the inside, if it was subtracted, you moved right, going more positive. But if it was added, you were going left because it was more negative. Yeah.
Has x minus c. You gotta move it. Wait, what was it? You gotta move it back to 0.
Mm-hmm.
So
fun fact, I'm glad you mentioned that. Just as a fun little aside, so I'm teaching 126 right now, and that's the section we're actually going over right now. And so with my students, I tried to explain that to them. It's best to see horizontal shifts as what they would do to the origin when y is equal to 0. So for y equals x minus 2 cubed, we would need to add 2 units to get back to a y value of 0. If it was x plus 2, we'd have to move 2 units left to -2 to get myself back to 0. That's the idea. So I'm glad that's the way I internalized it too. So it's a horizontal shift by c over b. If c over b is positive, it's going to the right. And if c over b is negative, it's going to the left. So hopefully that helps understand why the phase shift is c over b. Phase shift is just another fancy name for a horizontal shift. And because of the way mathematicians have decided to do this, I think it just makes it look prettier. You don't have to write as many parentheses, but too many people are afraid of parentheses. Parentheses are the best thing in mathematics. That's a lie. Functions are, but I digress. And then why is D the vertical shift? It has to do with what D would be. As a reminder, so I'm drawing it over here so you don't have to see it. You don't have to draw it yourself. If this is f of x, then the function y equals f of x plus 1, that's an adding 1 on the outside of the function. That means that you're affecting just the y value. The x value will stay the exact same, and all you're doing is you're adding 1 to the function or the y value, so it'll shift it up 1 or down 1. So in particular, like that. So if this was a sine graph, what ends up happening, and this is something you might have remembered when you talked about exponential functions and logarithmic functions. Do you remember with exponential functions like y equals e to the x, we had the graph and it looked like this, but it had the horizontal line through the origin? But then what we realized, at least I talk about it a lot in my class, is if you do a vertical shift, that line travels with it. And so the same thing's going to happen with the midline of sine or cosine. It's going to go up or down based on the value of d. Any questions on that so far? All right. And so we've gone over amplitude, we've gone over period, we've gone over phase shift, we've gone over vertical shift and stuff. The quarter period, that's going to be useful for the stepping stones. So I'll explain that in just a minute. And then the interval is the phase shift plus the period. So with this function right here, we can identify everything. The a value, is equal to 3. So that means that the amplitude is 3. Now, as a side note, it's positive and it's a sine graph. Positive sign go up, right? We go up when we start because it's a positive. Like if it's positive, it's not going to change. It's not going to reflect it. It's not going to reflect it. So it should follow the shape of a regular sine curve. Then your b value is 2, which means that your period is equal to 2 pi divided by b, which is 2 pi divided by 2, which is pi. And I guarantee you, if you look at this, take the difference between pi over 4 and 5 pi over 4. The difference between those two numbers is 4 pi over 4 or pi, 1 period. Next, we're going to find c. Now, c, is c pi over 2 or is c negative pi over 2? It's pi over 2. Now let's now that might be a little bit weird, but remember the I'm going to put this as a side note up here. It's an asterisk. The c is equal to pi over 2 because general form is a sine, or sorry, y equals a sine of bx minus c plus d. The minus sign. So it's just like, do you remember graphing circles and parabolas? Remember the vertex form of a parabola was a times x minus h squared plus k? And so when you tried to find the vertex, it was the h comma k. It wasn't negative h comma k. So you have to fit it into the right format. So this one is already written in the right format. So our phase shift, our c value is going to be pi over 2. So that means, wrong color, that the phase shift is going to be c over b. And once again, I don't think I explained this in this class yet. Nifty little trick in case you didn't know this about learning. If you have to memorize a formula, you can do it like the best way to learn it for free. This is for frizzles, is to do it by just rewriting the formula every single time you do a problem. It'll just start to click in your head. So you don't even need to like, even if you have to look it up and then write it, it's just free practice and memorization. So that's my encouragement, is to just rewrite it. I know I kind of talk about not trying to write as little as possible for avoiding carpal tunnel, but In this circumstance, I granted a pass. So in this case, that would be C, which is pi over 2, divided by B, which is 2, which is pi over 4. And it's okay if like we're dealing with complex fractions right there, not because it's because it's a fraction within a fraction, but as a reminder about this, if you want to see this in your notes, but you don't have to. But if I've got pi over 2 over 2, that's technically 2 over 1, right? And when we divide by a fraction, we flip and multiply. So this becomes pi over 2 times 1 over 2, which is pi over 4. That's the reason for it. I'll keep it up here, but I'll put it over off the side. Now I'm going to erase it when I need the space for it. So the phase shift was pi over 4. And you'll notice the original sine graph would start at 0, but this one, it's a positive. Oh, and so should write this? Let's use green. Positive implies a shift right. The right shift by pi over 2, by pi over 4 units. This is a lot of information, guys. Please give yourself some grace here. This is going to take practice. It's going to take a lot of practice. Any questions so far? So yeah, we're not graphing it yet, but we're identifying all the properties and seeing how they correspond. And last but not least, what's D? 0. There is no D. There's a plus 0 here. So D is 0. So there's no vert shift. On an exam, by the way, so I'm writing all this detail down. You would not need to write all this detail. Like, write it down what makes sense to you, but this is for our note-taking purposes so that when we're looking back at our notes, we're like, oh, okay, that's right. D equals 0. That means there's no vertical shift. I'm staying right on the x-axis. Okay. Any questions so far? A lot to go over. Then, the quarter period, the QP. So this is off on the side usually. I'm going to erase this now, but if you need me to put it back up there, just let me know. And then the QP, the quarter period, is equal to the period divided by 4. That's pi over 4. Now, you'll notice that we have these 4 key points, right? Let's use red to really highlight, or pink. We've got this point, this point, this point, this point, and this point, which on sine's original graph, this is a different sine function, but on the original function, that would be 0, 1, 0, -1, 0. They always, like every sine or cosine graph that you will graph, if you're graphing one period, it's going to have 5 points, 5 key points. And it's like stepping stones or stepping steps. Go up, then down, then back up. For sine, but for cosine, it would go start at the top, go down, down, up, up. It's always like this, like it's this matching game. So the reason why I talk about the quarter period is that there's a pro tip. I need to make that graph smaller so I can write all this stuff next time. Hopefully you guys are able to fit it in there. It's a mess, but there's a pro tip. What color haven't I used? Green. Pro tip. Sorry, no. Sorry, not the pro tip yet. I'm sorry. I jumped the gun. Quarter period tells you where your stepping stones will occur. Oh no, I already wrote that above. I'm sorry. I already told that it's used to plot your stepping stones. Excuse me, I'm sorry. There's a lot going on this page. But notice, this is adding pi over 4 because this is is 2 pi over 4. Pi over 2 could be rewritten with a new denominator by just multiplying by 2 over 2. It's 2 pi over 4. So we start with the phase shift. The next point is moving a quarter period. The next point, moving another quarter period. Because this is 2 pi over 4. Sorry, people watching the recording, you can't see this. From here, to find the next point, we go another quarter period. Because this is 2 pi over 4 plus another quarter period of pi over 4. It gives me 3 pi over 4. And then this one right here, this is 4 pi over 4. So we're going another quarter period and then another quarter period. So we do it 4 times. 1, 2, 3, 4. So that's kind of that weird thing, like that always messes with my head. I don't know about yours, but if I slice something 4 times, it gives me 5 pieces. You know what I'm talking about? Like if I have to slice something to share between my wife, my son, and I, 3 people, if I cut it 3 times, I'd separate into 4 pieces. So it's a quarter, but you get 5 points because you have a starting point and then you have the 4 points that happen afterwards. But I digress. And I always make them not equivalent because I'm bigger than my wife and much bigger than my son, so he gets the small piece. I'm kidding, he gets the biggest because he'll throw a tantrum otherwise. Amaya, you had a question? Or no? Brian.
So the quarter period, mostly used just to like give us guidance.
Yes. Yes. So Brian asked an excellent question. He was saying the quarter period is really, it's not any definition in the textbook. It's mainly a nifty trick that I've learned throughout my experience in mathematics to help me draw these graphs very quick. Is that the quarter period helps us find the key points where the stepping stones happen. Instead of having to go in and plug in like pi over 6 and figure out what that would be, and pi over 3, and then plug those numbers in, it would just be awful. And so the pro tip that comes with pro tip for starting a graph, starting a sketch of a graph, write the x values of your quarter periods with the denominator of the phase shifts. This is not going to make much sense right now, but once we start dealing with like, so it just so happened that our phase shift had the same denominator as our quarter period. That was a nice nifty thing that happened. That doesn't always happen. So to try and figure out what the next number will be, when you're starting out, it really helps to write it in the same denominator. So for example, like we can even put a little specific example if you have space at this point. As an example, if your QP was pi over 2 and your phase shift was pi over 6, write QP as 3 pi over 6. That's only to help you figure out where to plot the points. You'll see, like, this one's going to be later on. This is going to be for, let me look at the examples. Not this example, not that example. In 7 examples time. So this will mainly become useful in a moment, but it's just a nifty little pro tip if your phase shift and your quarter periods don't have the same denominator. Is it required? No. This is an optional bonus. Amaya. Yes. So what's happening there, once again, is I've got pi over 2, and I'm going to multiply it by 3 over 3 to get a denominator of 6. I'm going to cross out the 5 so it doesn't make it confusing. Because my quarter period had a denominator of 2 and my phase shift had a denominator of 6, in order to get my quarter period to have the same denominator, I need to multiply it by 3. If the phase shift was pi over 4, what would I multiply it by? Let me write that down. So QP, don't write this down, but if QP was pi over 2 and the phase shift was pi over 4, what would I write the quarter points as? To get the same denominator as the phase shifts. I'd multiply by 2. So 2 pi over 4. If the it becomes a lot more difficult if it was like 5 and 4. That becomes a little bit chaotic, but hopefully you never have to see that. I know I can speak with definitive sake to say that you won't have to do that on an exam for me. I'm not going to make it like it's going to be if it happens where you need to do this, it'll be a nice number that you need to multiply by. You don't need to you're not going to have to multiply by 5/4 or some awful number. So, okay. So let's look at the time where we were 12:12. We got 8 minutes. Perfect. So one thing I wanted to go back to sharing this this cool thing. Is there a question? Is something funny? I mean, I am funny, but Brian, you have a question? Okay. It's this one. Switching over for a second. I've got this. If you haven't used Desmos before, it's an awesome thing. It's beautiful. And so if you look at this picture that I've done, the solid red is 1 period. And so you can use this to verify your answers when you're going through your homework. If you want to make sure you get them right, you can use this formula that I have, this setup. This has made it with a bunch of different sliders so you can figure it out for any situation. So I want you to see, and then so the dotted line is just showing this function will continue on and on and on forever, right? It'll go on and on forever, but we're only really interested in 1 period. So the amplitude A, notice that if I make A bigger, it just extends the graph. If I make A negative, it flips the graph because you're reflecting across the x-axis. I'm going to bring it back to 1. For B, that's responsible for the period changing. That changes the period. So you'll notice if B gets larger, we're dividing, like our period gets divided by a larger number, which shrinks the graph. It makes it oscillate faster and faster and faster. But if I make P less than 1, it starts to extend the graph. Really, really long and stuff. And then C is the phase shift. So if I make C positive, you'll see that it shifts to the right. So the graph, it doesn't look like it's changing too much, but remember, we're following what's happening to the red line, the solid red line. So when my C value is, oh, oops, that's supposed to be a minus C. So sorry. I know, it's terrible. So back to 0. So if the C value is positive, you see that you start shifting to the right. Whereas if your C value is negative, you start shifting to the left. All right. And then last but not least, D, it goes up and down. Whee! Any questions on that? So this is a very, very useful trick to kind of hopefully this is helping you visualize it a little bit better. It's a fun little thing to show your friends this weekend. I highly recommend it. TikTok, who, right? No, this is the cool stuff. Guys, like as soon as your friend says, "Dude, check out this video, this video I stitched on TikTok." No. Check out this Desmos thing. Very fun. Okay, back to the notes. So we're gonna start. We're gonna go through and graph all the different setups and identify all the pieces. Looking at the time, we got 5 minutes. I think we have enough time to do just one. That's okay. now that we've got all the understanding, I'd recommend, like if I could ask something of you, so it is, Monday is off, it is President's Day, so you have it off. If you could go back over that previous page, just kind of refresh yourself, please, I recommend it. It'll make Wednesday's class so much easier because you'll have that fresh in your mind and it'll be better to work with. But either way, so this first one, this is sine equals 3x, or like y equals 3 sine of x, excuse me. So you could rewrite that to get it into the sinusoidal form to be 3 sine of x minus 0 plus 0. Now, I'm writing this for our notes, but on an exam, you don't need to write that. That's just for us to realize we can identify all the bits and pieces. A is 3, which means that our amplitude is 3. And this is a sine graph with a positive one. So will it go up or will it go down? It'll go up. It'll start by going up because it's a positive. Remember, if you're positive, you're feeling up. You're feeling good. So positive. So positive sign. Go up first. Go up. B. What is B here? There's no B value. Yes, there is. It's 1. There's the implied 1. The mathematician's very, very lazy. We can avoid writing extra stuff we typically do. Mathematicians, that is, not mathematics educators, but mathematicians. So B is equal to 1, which means that the period is equal to 2 pi divided by B, which will be 2 pi over 1. I'm going to draw, I'm once again, I'm writing 2 pi over B to make myself get free memorization. It's just for frizzles, as the kids still say. Do you guys still say frizzles? You should. It's an awesome thing to say. C value is 0, so there is no phase shift. And the reason for that, we can write that down. Reason, the phase shift is equal to C over B. That'll be 0 over 1, which is 0. If your C value is 0, the reason why I think about it is thinking about it as a linear transformation. If I don't have a number there being added or subtracted, it's not going to move left or right. And last but not least, D is also 0. So that means no vertical shift, no VS. Or we can just say vert shift. Good so far? Any questions? We've identified all the pieces. On an exam, if you write all those, like identify the A, B, C, and D, that's worth some partial credit. Even if you can't figure out the graph, that's worth some partial credit to me. So the key points, or maybe I think I'm going to call them stepping stones. Stepping stone points, stepping stones. Start at the phase shift, which is 0 here. And then we're going to increase by the, I meant to write this here. I'm sorry. I forgot to include it. The quarter period, QP, is the period divided by 4. You don't even really need to memorize that one, though. That's just the language. A quarter period would be a fourth of the period. Take the period divided by 4. So that's one you don't have to have memorized. It just, luckily, this is a situation where its name means what it is. So that would be 2 pi over 4, which is pi over 2. So to find the key points, you start the phase shift, and then you just keep adding the quarter, the quarter periods until you get to where you need to go. So, wait, no. Plus pi over 2 gives me pi over 2. Then pi, or 2 pi over 2, rather. And then just pi. 3 pi over 2. And then that's 1, 2, 3, and then 4, and that's where we'll stop. To 4 pi over 2, which is 2 pi. And I realize I've gone over, so I we'll finish this up next time. I don't want to. I know it's a bummer to leave on a well, no, it's a good thing to leave on a cliffhanger. Yes, Brian. Next to phase shift, right here, or above it. So I'm writing, this is the first X value you're going to do. Then to find the next point of your stepping stone, you'll add a quarter period, then add another quarter period, then add another quarter period, then add another quarter period. Is that okay? Yeah, those are our stepping stones. Those are up, start at 0, up 1, down, up for sine, or up, down, up for cosine. Yeah. All right. That'll do it for today. If you guys have any questions, feel free to email me. Remember, you don't have class on Monday. It's President's Day, but please try and review this before class on Wednesday. You'll be thankful that you did. Otherwise, you guys have a great rest of your day, a great weekend. Try to avoid the endless scroll because social media companies are trying to steal your attention for money. They're trying to steal it. So please don't let them, and have a great rest of your day.